humankind right from the beginning. And the invention of the wheel more than 5,500 years ago in Mesopotamian civilization that was there in today's Iraq. Man's dealings with materials have been revolutionized. And they have come a long way today. And pioneers like Sri Ranga Rao Garu, a professor of eminence from IIT Madras, have taken to nanotechnology, the material science, so that our existence as human beings could be that much more comfortable. And I am happy and I am glad that our departments of chemistry, both from ASC and Dept, have found it fit to organize this national conference on recent trends in materials science. And I am more than glad and grateful to God that Professor Andhra Loyola, our own alumnus of 1978 and 81 batch, as he passed out of the portals of a college, I completed my junior intermediate in the same college. He is the chief guest and the keynote speaker at the inaugural of this national conference. He will be duly introduced to you, dear students. He is one of the pioneers from our country in nanotechnology and materials science. A scientist of international repute from the most eminent IITs of the day, that is IIT Madras. And it is my privilege and honor, sir, to welcome you into the lap of your own alma mater. I also take this opportunity to welcome all those people who shaped our chemistry department to be what it is today. And we have a few of them in the persons of Sri Shankar Rao Garu, Ram Sastry Garu, Dr. Vai Hanumantarao Garu, and others. And the present members of the chemistry department headed by Dr. Anita. I extend a special welcome to you, sirs. And dear students, researchers, and the invited speakers who will be coming, the paper presenters, it is my bounden duty, though many of you may not be present here right at the inaugural, to welcome you and wish you, praying that all the interactions that take place in this national conference will be enlightening and enriching for the progress of the humankind. Thank you and welcome each and every one of you.
Thank you very much, Father, for your very warm and heartful welcome and blessings towards this national conference. Now, I invite Dr. G.V. Ramana, the convener of this national conference, to give away the aim of the conference.
Today's chief guest, Professor G. Ranga Rao Garu, IIT Madras, Reverend Father Kishore, Principal, Andhra Loyola College, Reverend Father Zagaya Rams, Correspondent, Andhra Loyola College, Dr. P. Anila, HOD of our Chemistry Department, respected senior faculty members, Professor V.R. Shankar Rao Garu, Professor K.V.A. Ram Sastry Garu, Professor Dr. Vai Hanumantarao, respected faculty members from other colleges and universities around India, my dear colleagues, dear research scholars, and my dear students, good morning to you one and all. It is a great honor and a pleasure for me as a convener of this national seminar, Recent Trends in Material Science RTMS 2K23, to invite you all to join with contribution to this national seminar. The national conference include keynote speeches, invited talks, which will be delivered by distinguished scientists and professors from academic institutions, and oral presentation by delegates and poster presentation by young junior participants. The conference strives to provide a unique theme, shaping future by contributing knowledge and innovations in material science. It aims to provide scientists and experts to stay abreast of this rapidly changing field by offering a comprehensive overview of recent findings of material science. This national conference RTMS 2K23 covers all aspects of material science, engineering, advanced smart materials, and other topics. This conference serves as a bridge among scientists, researchers, experts in research for the development and production. National scientific activities are big platforms for scientists, academicians, and young students from all over India to interact and communicate with each other. It believes that this national conference RTMS 2K23 will provide an opportunity for delegates from different cultures and states to interact with each other. Also, this conference will be performed successfully in favor of qualified scholars and experts, and will be very beneficial for the young delegates by encouraging them and improving their confidence of presenting research in a national platform like RTMS 2K23. I am pleased to invite prospective scholars, academicians, and engineers to submit their original contribution to this important conference. You are sure to have a meaningful experience here with the scholars and experts from different cultures and states from all over India. With these few words, once again I am inviting guests and all the delegates to this national conference 2023. Thanks to one and all the best.
Thank you, sir. Thank you very much for explaining in detail the aim of this conference to all gathered here. Now, I invite Dr. P. Anila ma'am, the Organizing Secretary and HOD Department of Chemistry ALC, to give away the dynamics of the conference.
Dignitaries on the dais, Reverend Father Dr. M. Sagaraj, SK Correspondent, ALC, Reverend Father Dr. G. P. Kishore, SK Principal, ALC, Distinguished Chief Guest, Professor G. Rengarao, sir, esteemed former colleagues of my department, professors, research scholars, my faculty colleagues, and my dear students. Greetings to you all. On behalf of the organizing committee, I once again welcome you all to this gathering. I appreciate the presence of each one of you. I acknowledge and value the presence of our chief guest who came here to address us despite his hectic schedule. I also like to thank the management, especially Reverend Father Correspondent M. Sagaraj and Reverend Father Dr. G. P. Kishore, Principal of our Loyola College, for their continuous support and cooperation. Even in the absence of Reverend Father, Francis Xavier, Reverend Father Dr. K. Francis Xavier, Director of Andhra Loyola Institute of Engineering and Technology, I have to thank him because he has collaborated with us, supported us, and presented this event to a broader audience. Our sincere gratitude goes to the all vice principals. Even in the absence, I have to call them. Reverend Father, I, Raj Father, Reverend Father K. Anil Kumar, Reverend Father Dr. Y.T. Prabhu, for extending their help in whatever way they can. Before going deep into that conference details, I once again thank all of you for coming over here, and your presence adds happiness to us. Thank you, sirs. One of the fundamental elements in creating modern technologies has always been the ability to develop new materials. Material science is a field that concerns with preparing new materials, characterizing it, and testing the different materials. The material science is a science of making materials, and one fundamental idea that underpins material science is a correlation between the material structure and properties. There comes the importance of chemistry. Material science is a multidisciplinary area, and it is a blend of different sciences and engineering. In the modern world, applications of interdisciplinary field are becoming increasingly important, and that's why we have chosen this specific subject for our conference. RTMS 2K23 aims to bring academicians, researchers, and students to exchange and share their knowledge related to material science. It also provides a platform to present and discuss the most advancement in material science. The RTMS 2K23 is scheduled for 2 days. Today is our first day. Immediately after this inaugural session, after the break, we will be addressed by our chief guest, a renowned professor with expertise in nanostructured materials. Sir will give away the keynote address. 2 more invited sessions will take place following lunch. The first invited talk is from Dr. Retin Rajan, Marivanes College, Thiruvananthapuram, and the topic is relevance of surface reactions in interstellar chemistry. The second invited talk is from Dr. Sambat Kumar, Department of Chemical Engineering, NIT Warangal, Telangana, and the topic is recent advances in high-grade supercapacitors. On day 2, that is tomorrow morning, we will include some paper presentations and a requested address from Dr. Naresh Kumar, School of Engineering, University of Hyderabad. And the topic is morphological features and photoluminescence of zinc oxide and zinc oxide decorated SN dot layered graphene. In the afternoon session, we listen to Dr. Pradeep Kumar Brahman from KL University in Devada about the topic development of biosensing and technology. And after that, we shall move on to the closing ceremony. I hope this seminar broadens the understanding of material science and provides all the participants with a valuable, successful, and productive experience. Once again, happy greetings to all of you. Thank you.
Thank you very much, ma'am, for the detailed explanation of the dynamics of this conference. Now I request all the dignitaries to proceed towards the release of this souvenir. So we are going to release the souvenir now. So kindly I request the faculty members concerned to be here and let all the dignitaries proceed towards the release of the souvenir.
Please give a big hand while we are releasing the souvenir. Please with the support of all of you that we are releasing the souvenir.
Thank you very much. Now I request Dr. C.H. Bhargavi ma'am, Department of Chemistry ALC, to introduce the chief guest to the gathering.
Reverend Father Dr. M. Sagairaj, SJ, Correspondent, Reverend Father Dr. J.P. Kishore, Principal, our esteemed Chief Guest, Professor G. Rangarao Garu, IIT Madras, Dr. Anila Madam, HOD and Organizing Secretary of this present National Conference, Dr. G. Ramana Garu, Convener of the present National Conference, respected faculty members and dear students, good morning. So it gives me immense pleasure to introduce our illustrious chief guest, Professor G. Rangarao Garu, IIT Madras, Department of Chemistry, IIT Madras. He was born in Krishna district, Andhra Pradesh. In 1960, he was student of Andhra Loyola College. He did his BSc in 1978. During 1978 and 1981, he earned MSc from IIT Bombay and PhD from Indian Institute of Science, Bangalore. Following various postdoctoral appointments and fellowships in Italy, Japan, France, and Germany, he joined the Department of Chemistry, IIT Madras in 1996. His research interests include synthesis and application of nanoscale materials and POM-based ionic liquids to heterogeneous catalytic processes, solid-state electrochemistry, energy conservation and storage. He was honored with the STA Fellowship Japan, CNRS Fellowship France, TIAD Fellowship Germany, and many more. He is visiting professor of Institute of Molecular Science Japan, University of Augsburg, Germany, University of Trieste, Italy, and he guided 15 PhD students and published 180 research articles in various national and international journals. He has the Google Scholar HLX 48 and 9,921 citations. He established Solar Fuels Laboratory as part of DST Solar Energy Harnessing Center in IIT Madras. The above achievements speak volumes of his zeal for his scientific research. Here, I now present Professor C. Rangarao to the august gathering. Sir, I welcome you to give your keynote. I welcome you, sir, for the felicitations.
Now we shall proceed for the felicitation of the chief guest by the management. I request all the fathers and the ma'ams to kindly felicitate our chief guest, Professor Rangaram sir. So kindly give a big round of applause, students, as the conversation is. It is a very proud moment for us because he is an alumnus from our own college. So we feel very proud for you, sir. Thank you very much for coming up in front of us, sir. Thank you so much.
Good morning. ముందుగా మా గురువు గారు రామశాస్త్రి గారు శంకరరావు గారికి నమస్కారం. సో నేను ఈ రోజున ఈ కాలేజీకి సందర్భంలో రావడం ఇట్స్ ఎ గ్రేట్ ఈవెంట్ అన్నమాట. దానికి పునాదులు ఏంటంటే సో విత్ దాట్ లెట్ మీ జస్ట్ addressing begin with I would say the Reverend Father P. Balachaudhary, Reverend Father Dr. Kishore, Reverend Father Dr. Sagaya Raj, Reverend Father Dr. A. Francis Xavier, members of organizing committee, Dr. Anila, Kapana, who interacted with me to organize this, and faculty members. I see some faculty members here, and students. I see a lot of students here. Very happy to see all of you. Andhra Loyola College and probably other colleges also in Vijayawada, and participants of this conference. It's a, I mean, I'm just so excited to come to my college. I still consider this college as a college which was a stepping stone for me to do a lot of things in my life. I'm very pleased to be present here today and to participate in this conference and also meet all of you here. I must say, I'm a proud alumnus of Andhra Loyola College, and I was here in, as I said, she mentioned, 1978-81. I remember I gave an interview here. Subbarao, organic chemistry teacher, I interviewed him. The question that he asked, I still remember, was what is the chemical bond in NaCl? Perhaps I didn't answer him properly, but I probably tried, so he perhaps got impressed. Okay, he's trying. I met him a few years back in his house. I think he is no more now, but so that is how I entered into this college. I would actually like to recall many of my memories in this college. Particularly, I must recall my teachers, starting from Ram Sastri Garu, Subbarao Garu, Shankarrao Garu. They are all basically chemistry students, chemistry teachers for us. And then physics, Basavanai Garu, I don't know how many of you know, he was a physics teacher. And then Bolai Garu, he was also physics teacher. And then Sastri Garu, mathematics. He taught me linear algebra. I still remember that course. Of course, it was a difficult course, but he was an excellent teacher. I still use some of those principles now. And Kameswarrao Garu, he was also a mathematics teacher. Then Metta Venkateswarrao Garu, Telugu teacher. Excellent Telugu teacher. He knows that I asked him to Telugu Nagustundante, I am సో మాతృభాష మర్చిపోకండి. తర్వాత లక్ష్మీనారాయణ గారు ఆయన ఇంగ్లీష్ టీచర్. సో హీ వాస్ ఎక్సలెంట్ ఇంగ్లీష్ టీచర్. సో there are many more. I'm not able to recall now. All these teachers, they were gems. They were gems. We were taught so many chemistry concepts in the college. And then I still remember that library where first floor or second floor, I don't remember. I used to go and sit down there and read. There were only 2 or 3 books. Morgan and Boyd and I.L. Pinnar, 2 volumes were there. Those are the books I started reading in that library. So that's how the chemistry started developing in my mind. This college has been a great learning center, let me tell you that. Because getting an admission in this college was very tough. I was actually one of the luckiest persons to get into this college and then have good teachers teaching me. And this college was actually very well known for its discipline, time management. These are all important in life. Punctuality, and then very good library where you had fantastic textbooks and magazines also. Even newspapers, I remember even newspapers were there. We were actually reading those newspapers as well. And then there was nice sports and hostel facilities. There was a lot of playground was there outside. In one corner, I think it is still there. That's where we used to play. So these were the beautiful things and excellent things we enjoyed those days. I am sure you have much more better facilities now in the campus. And let me tell you one thing, those students, those days, even now also I am sure, the students were very sincere and hardworking. In Loyola College student goes anywhere in Vijayawada, they used to say, oh, Loyola from Loyola. There was some special compared to other colleges. That was the thing which we enjoyed. And just to recall, Ram Sastri Garu, he used to conduct in-house experiments for chemistry, chemistry events. Actually, the college used to conduct city, the chemistry events, every year. That's how I remember. And he used to demonstrate us chemistry experiment, just outside that chemistry lab. That wing, that is right side thing. So I still remember those things. And the experiment that he demonstrated, I still remember is potassium chloride and sulfuric acid. Sulfuric acid. What happens? So it was a fire. The fire comes out. It's a beautiful experiment. I still remember. He is making similar things. Lot of those experiments. They are available on YouTube. He sent it to me. I saw many of them. Very interesting experiments. Some of you can see that. In fact, I told my research scholars, go and look at those experiments that were loaded in the uploaded in the YouTube. And then that's how the lot of the experiments were demonstrated in this college, particularly in the chemistry department. And also, I remember father. I think I don't remember maybe Ram Sastry Garu. So there was chemistry teacher, Father Joe. No, I don't remember his name.
Joe D'Souza.
Right, Father Joe D'Souza. He was actually doing research. There was a small research lab there. He used to make something. There was some small equipment that used to be there in that third floor, I think, somewhere. And we used to peep in what actually is going on in those labs. So that was an exciting thing. We were very curious to see what he was doing. So the important point is there was a trend in Loyola College for students to write competitive exams. The teachers encouraged us a lot to write competitive exams to go to IITs, in colleges, science colleges, IISc, University of Science, many places. We were actually more aware those days of different institutes in the country. That was also a very, very positive thing that we had. That's how we came to know about IITs and others. Those days, now I think everybody knows. But those days it was very hard to get any information. So we were aware of all those things. That's because of the teachers that we had and the day encourages clockwise those days. So remember, I always you are just starting your young student. My academic career or anybody's academic career would not have been possible without good teachers and supportive mentors. So you should have a mentor, good teachers, parents, and a bit of luck is also important. A bit of luck. I think I had quite a bit of luck to be here. Right? So that is very important. But your hard work is the one which pays you, a lot in the years to come. So from there I actually joined Nagarjuna University after this because my father could not afford my education. So he said somewhere nearby. I went to Nagarjuna University, but then I moved out from there to IIT Bombay, and then there I had again great teachers. Some of them are still alive. And then from there I went to IISc Bangalore. How many of you know Professor C.N.R. Rao? Raise your hands. Professor C.N.R. Rao. He was my guide in IISc Bangalore. Right? So he was here. He's a taskmaster. He works 24 hours a day. He doesn't sleep. He's a taskmaster. So that is how we got inspired there. Then after PhD, went out and then learned a little more what's going on in other countries, other labs. Get more knowledge and then come back to IIT and then started the career. That is my path. But you can have your own path. You can define your own path. Okay. In those days, this kind of seminars were not there for us. We had no experience of what seminar was like. Nowadays, you should thank college authorities to, organizing the seminars so that we are all exposed to latest developments in research and then education. So I see that Loyola College morning I went for a walk and it's expanded now. I think we have engineering technology institute is there and a lot more facilities I see there in the campus. So one of the important things that I wanted to tell you is
Those days, there were only few options what we could choose. But these days there are a lot of choices. But be clever to choose what is your interest, and then try to focus in that area, in whatever the interest that you have in your mind. That's very important. You need to identify what it is. But whatever it is, today we have internet, we have many things, many ways, many communications. That cell phone gives you everything. What is happening in the world. But there, you need to see what you need to pick. Good things, which is useful. There are a lot of things which you get attracted, but you waste your time. Don't get attracted to wrong things. Look for good things which are important for your growth. Whatever it is, but today what is important is, the teaching and learning remains core, both for students and teachers. That is something which you can never replace that. Okay? And textbook reading is always good, to some extent. Okay? So that is the basically Loyola College has excelled in learning and teaching and learning area so much that the students who actually graduated from this institute has benefited a lot. You can see not only me, there are many people who are in very high positions in the country. Okay, coming to the scope of this conference, this trends in material science is a vast area. There's a lot of this is an umbrella kind of a thing, but there are so many aspects of material science that you can think of. So it is actually connected to, it is a highly interdisciplinary area. It is connected to chemistry, physics, mathematics, engineering, biology, etc. Okay, and you can actually do your material science and then find applications in variety of these areas. The previous speakers have mentioned so many areas and applications. Now the important thing here is, a few things which I wanted to point out here is that scientists, the people who are working in materials chemistry or materials science, they always try to look for making new materials, preparing new materials, new molecules, and then see what they are useful for. Or if you have an application, this is an application, I want to have a material, people using their chemistry knowledge and material science knowledge, try to, in physics knowledge also, try to make a material which is suitable for that particular application. So either way, it is impossible. Okay? So currently, once we make this material, new material or new molecules, you need to see what that material is. So you make a powder, if you have a powder in your hand, you don't know what it is. So you should know what it is. So for that you need to use spectroscopy, microscopy techniques to characterize that, to understand what that material is all about. And then see, once you understand the properties of the material to some extent, then try to see where you can apply that material. Okay? So you need spectroscopy techniques. I'm sure you may have a course on spectroscopy techniques. If you do not have, I would actually suggest the department teachers to organize a spectroscopy workshop exclusively for students. That will be beneficial. Now, having made these new materials, which is the topic of this seminar, you need to have new materials for few important things. One is energy. Remember, energy is going to be a very serious problem in future. All the oil, everything will disappear. Another 20-30 years, already oil cost has gone up all the way from 50 rupees to today it is 110 rupees. And oil will not be available in another 20-30 years. You will all face depletion of oil. So what we need to do is we need to find out materials which you can actually convert CO2. We have a lot of CO2 coming in the atmosphere. The CO2 needs to be converted to fuel and then reuse it, and then it's a cycle basically. So you need to have a material which can actually do the job efficiently. So that is one of the aspects. And then all of you know ammonia Haber process. Now ammonia Haber process takes a lot of energy. It's a very high temperature process, 400 degrees centigrade, and then very high pressures. So it consumes a lot of energy. People are trying to now convert nitrogen to ammonia at room temperature. So that is one of the challenging things. If we can find out a material which can actually do the job at room temperature, that will be a great achievement. That is second thing which I wanted to tell you. The other one is green hydrogen. You must have seen in the newspapers, our Prime Minister has announced something like 20 to 25,000 crores for generating green hydrogen in India. So now in Andhra Pradesh is one of the places where they wanted to set up something like this. And then in Kerala, IIT Palkar, Kerala, they are actually already setting up green hydrogen valley, where the idea is to produce hydrogen by splitting water. See, where is hydrogen? What is the source of hydrogen on Earth? One is water, the other one is hydrocarbons. These are the two sources. So you are already extracting hydrogen from hydrocarbons, which actually releases a lot of CO2. So the green process is basically green hydrogen is you produce hydrogen without releasing CO2, without contributing CO2 to atmosphere. Because of CO2 temperature is rising and so on and so forth. I'm sure all of you know that. Environmental problems we have. So water splitting to generate hydrogen, which should be green hydrogen, without producing any CO2 in the process. So that is one of the things where a lot of materials chemistry, material sciences research is going on. Then energy conversion storage. Now we have a lot of batteries, but then there are new devices are coming out as supercapacitors. I'm going to talk about that. After one more stage, we're going to talk about that. Now, can we replace batteries with supercapacitors? So that is a question. So that's where a lot of materials are required. So people are trying to develop these materials. Of course, these materials have strong applications to biochemistry, biology, etc. Okay. So these are areas which are currently important. I think some of you who would be interested in research, etc., you can actually look out for literature and then get yourself get to know the topic more better. But what is important is also when you are actually making these materials, some of these materials can be toxic. You have to ensure that they are not toxic, they are sustainable. You make a material to work at least for about 10 years, for about a decade. So the sustainability is also important. Sustainability is also important. So we make so many things, ultimately you have to dispose them. Another 10 years down the line, all the electronic items that we made, many of them have to be disposed. We don't know how to do that. You enjoy it now, but 10 years down the line will become a problem how to manage those things. So this sustainability is also very important, important thing to keep in mind in materials research. So I am sure this conference covers some of these aspects, and I wanted to congratulate the organizers, the college, authorities, principal, and also the participants. To have participate in this conference, and I wish all the best and successful seminar conference, RTMS 2K23. Thank you so much. I hope I'm not taking too long time. students here again. It's very nice. So I'm going to introduce a topic here to you. Inorganic material for energy storage. So if you know G20, all of you are aware of G20. Now the government of India is saying everybody is put G20. We are leading this G20 this another 3 years. Okay. So as I mentioned to you, energy is going to be a very serious problem in the coming years. For two reasons. One is the energy that is produced currently is going to give a lot of CO2. It's actually pumping a lot of tons and tons of CO2 into the atmosphere. That is actually warming up our atmosphere, and then we are getting a lot of environmental problems like cyclones, etc. So this is very important to cut down CO2. Second thing is this oil, which I am going to give you here. Let me just show you that. Yeah. Oh, before going there, I wanted to share with you. This is the Loyola College in 1980. Okay. So you can see these are the buildings. This is our chemistry labs here. We had chemistry labs here. Mathematics, we used to go somewhere here. And then you have these two hostels. And then this is another hostel. And this is the place. You can see all this. This is the place where we used to play. And then in afternoons, evenings, we used to go sit there and study under the trees. Right? This is the prayer hall. We used to go there. And this is the road where we go to Bandala. Right? How many of you remember that? All of you know this, right? Now it has changed a lot. I may not be able to recognize it if I go there. I even know the place where I stayed. Okay, so that's a. So what we did, I don't know who took this picture, but I have this picture with me. I also had another picture with my teachers, but somehow I missed to keep it here, where he was also there. Okay, just to recall this. So, inorganic materials are energy storage. As I said, energy. Now we have to look for oil, etc. in the different story, but we have to look for renewable energy, that is sunlight. This energy has to be extracted and stored. For that, we need to develop materials. So that is a challenge that we have. So there are several variety of things available, but what I am going to give you is a brief history of what is energy storage and why it is important, and then a couple of examples like metal oxide, calcium metal oxide framework. These are the two topics which I am going to cover. I don't think I have time to do this. It's a little longer one. So next one. Okay, this is a slide which my students prepared. These are the different areas which I work in my group. You can see the photoelectrochemistry. We worked on this layered materials here, and then we have CO2 absorption reduction. This is another one, and these are the solar capacitors where energy storage devices are. We work on that here, and then here this is a hydrogen generation using water splitting. And this one is electrocatalysis, particularly for fuel cells. We need electrocatalysis for fuel cells. And then this is the nitrogen reduction. Nitrogen reduction at room temperature. Vapor process is high temperature, high pressure process. So we wanted to see whether we can actually reduce nitrogen at room temperature. This is polyoxometallics, ionic liquid. Some of you are working in ionic liquids. Some faculty are working here in ionic liquids. So these are the generally areas where my students work in my lab. So I am going to focus. I am going to talk about this part today. This part. Okay. All right. A few examples. So I just wanted to tell you that James Compton said, a storage did not end for lack of stone. Stones are there today, but storage is gone. Similarly, the oil age will end long before the world runs out of oil. Oil is, without oil, nothing moves now. Oil is the energy that we are using, petrol, diesel, natural gas, so on and so forth. So this is going to be coming to an end, or it's going to be very expensive in the future, in another couple of decades. All of you will face that. Okay, so we need to look at the future of energy, energy from sun. The energy that we have, lot of energy is coming from sun. Whether we can actually tap that energy and then store it and use it. So this is the important thing that we are actually looking at. Okay, so that the humanity can actually get an unlimited energy source for their daily needs. So here we need to have the materials, nanomaterials or any other materials, and then synthesis of that and develop the technologies related to that. You get the good energy storage materials and technologies industrially, which can be used in industries, so that we have secured energy in future. Now, if you see here, we are all familiar with this. We have so many gadgets. Many of us have this. These cell phones and so many fuel cells, batteries we use, capacitors. These are different ways of energy storage that is happening now. But here, the energy storage, energy which is coming from sun, is something which has not been tapped extensively. So energy is definitely very important for us, for our life. Every day we need energy. You can see the amount of energy that is consumed here in this graph. You see here, this is in terawatt hours. And you see this is 1800, here 1800. This is 1900, this is 2021, couple of years back. Until 1900, the amount of energy used is very less. So starting from 1900 to 1950 also is almost not very significant. But 1950 around, we can see tremendous increase of using oil, coal, biomass, natural gas. Now natural gas is also increased. And this is the one which is currently driving us, using us as a source of energy. And this is going to be depleting very fast. And then we will have to now worry about even we can have other ways of producing energy, particularly when you look at renewable energy. Where renewable means you can actually renew it. It's not going to be over. I mean, if you take oil, you burn it, it is gone. But the renewable means you will be able to keep using it. Okay? So that is one of the renewable energy is sunlight and biomass. Okay? So this is something which, but sunlight is only during the daytime you need to store it. So you need to have batteries, for example, or capacitors. These are the things where you can store this energy. So you need to have materials to develop efficient devices like that. It's working. Okay. So now here you can see that all of you are familiar, cell phones, laptops, digital camera, tablets, wearable devices. Everywhere you use a battery, right? Do you have battery or not in your cell phones? Right? So you use batteries here. But in future, can we replace batteries? Let's say with what is called a capacitor. For example, I am giving you a table here, energy storage devices. This one is capacitor. Capacitor means solid capacitor. In physics, you must have learned capacitor, right? You have a course and you have a dielectric fitting. Some of you must have learned that in your BSc. Right? So here, it charges very fast, and then it also life cycle is about 10,000, 100,000, and then its capacity is very small, around 2 millifarad. And energy density is low, power density is high. But then with supercapacitor, you can use it, you can still store it, very fast. You can also use, the capacity is very high here. 1500 farads, you can go all the way up to 1500 farads, which is really very, very high. But the drawback here is energy density is low. Right? And a battery, we have been using batteries. Batteries have high energy density, but power density is low. What it means is, it does not pump power immediately. It just takes longer time to charge and longer time to discharge. Whereas the supercapacitor, it is very fast it will charge and it is very fast it will discharge. Okay? What we need to have is something like this. You need to have both high, the high energy density, the high power density, both are required. So for that you need to develop materials. That is the task that we have. Okay, so this is the plot where you have capacitors, there is resistor capacitors. You can see the power is very high here, but energy density is very low here. Whereas if you take batteries, fuel cells, energy density is very high, but power density is very low. You see the graph here. But what we want to have is combine both and then take electrochemical capacitors towards this side where you have good power density and energy density both. That's what actually now a lot of work is going on. Okay. So what we can have is, can we have reasonably high energy densities like batteries and excellent power density like conventional capacitors here, and then cycles millions of times. You will be able to recycle it. Just charge, discharge, you will be able to do it millions of times, unlimited. So that you can use it for at least 10 to 12 years of life. You buy a capacitor, it will work for a decade. Then only you will invest money. Otherwise, why would you buy that? So these are the things which you need to. And then high rates of charge and discharge. In seconds, you will be able to. You don't have energy in patience in the energy temperature. Everything will be done quick. If it goes, you have to lose interest. So it has to suit your interest as well. Okay, the task is to develop materials that might combine high energy density and then like batteries and then long cycle life and short charging times. Some of the cell phones, earlier we used to charge them for about 1 hour, 2 hours, right? Now we can charge them in about 10 minutes, 15 minutes. Very fast, right? Things are changing very fast. So, what is this supercapacitor? Capacitor is normal capacitor. Supercapacitor, can have very high energy, right? So that is electrochemical in nature. So here we have different types of capacitors are there. This is the AA capacitor, pseudo capacitor, hybrid capacitor. Hybrid capacitor, I think somebody is talking tomorrow from NIT Warangal. I saw that somebody is talking for hybrid pseudo capacitors. He will be able to give you more. So here what happens is AA capacitor is simply you have an electrode, you have an electrolyte, and this electrolyte ions will go and absorb on that, and then the capacitor develops there. There is a charge developed there. Okay, right? So similarly, in the case of pseudo capacitor, the ions will go and react with the surface layers. That means you have parallel reaction. That means oxidation reduction reactions take place there. That's another way. That is another way of storing energy. Absorption or reaction. Both the ways you can store energy. If you are using this redox pipe, then you call it as pseudo capacitor. Here you have conducting polymers, metal oxides. These are some of the examples which are applicable to this particular pseudo capacitor application. And the electrical double layer basically carbon-based materials. Carbon don't react so easily, but they absorb. You can see that carbon is used in candles, to clean. So that only absorption takes place. There is no reaction. So it's only absorption. So that is that's called electrical double layer capacity EDLC. Okay. The kinetics is this is surface control kinetics, whereas here this is the diffusion control kinetics. Okay. So the kinetics of the interface are slightly different. Okay. So this is already we are talking about micro supercapacitor, not the big one. Micro supercapacitor to fit into the electronics. Now see, you can see this nice graph here. What is the difference between battery and rechargeable battery and supercapacitor? You see, this is the discharge, this is charge. You see the time here. This time is very small, right? So you can charge. So you have high voltage, you discharge. This happens only in a very short span of time. Whereas here, this one charging takes takes a lot of time. See, charging takes from here to here all the way. And discharge also takes that much of time. So it is slow process, it's not fast. It's a slow process. So what we need to have is, you need to combine this and this, find a material which can do both. So that you can use it as a battery and capacitor as well. Okay, how do we know what is this pseudocapacitor, supercapacitor? I think what people do in the lab is they use what is called cyclic voltammetry. Voltammetry, have you heard of it? Voltammetry. Cyclic voltammetry. Electrochemical method. So using that cyclic voltammetry, you can actually measure the time versus potential curves or potential versus current curves. So if you get this kind of curves, that is indicating it is a supercapacitor. Whereas if it is indicating this kind of curves, whereas you have this curve, this is nothing but a reaction that is taking place in giving current. The current comes when there is a reaction, right? Okay. So this is the current which is potential or even current also. Here also you can see there is current potential current is also there. There is a peak here. That peak indicates there is a reaction taking place on the surface. Right? So in this case, you can actually see this is a basically here you have Faraday process, that means the cross reactions are taking place, whereas the non-Faraday process only the adsorption is taking place. So by using these methods, drafts, one can actually figure out what kind of material is that, and then what we can use it for. Okay, this is what it is. So here, this is only adsorption, whereas in this case, there is a reaction taking place, and here there is interconnection taking place. Interconnection means, if you have graphite layers in between, you can insert ions. So that is also another material, kind of material which can be used for charge storage. Particularly lithium-ion batteries are similar to that. Okay, just look at what is the supercapacitor. Nobody, actually, this is only known to the physicists mostly. Because when you open your laptop or computer, you see that the capacitor is not working, so they will tell you. That is a solid-state capacitor. Right? What we are talking about is electrochemical capacitor. Right? So, in 1962, the first time people thought about electrochemical capacitor. Then people have looked at 1971. People have identified ruthenium oxide as a material for supercapacitor, electrochemical capacitor. 1971. 1987, the pseudocapacitor is connected polymer. People started looking at poly is a polymer, connecting polymer which they have used to make the supercapacitor. 1995, again ruthenium oxide, hydrous ruthenium oxide, not just ruthenium oxide, hydrous ruthenium oxide is found to be a very good material. Then you go to 1999, manganese oxide, 2000 vanadium oxide, and then lithium cobalt oxide. See, now and then starting from 1962, 2020, now we have vaccine materials. New materials have come up into the research and market, vaccines. But you can see now how research has actually progressed to identify a variety of materials that are present here. So we entered into this field because one student who said, I will work in this area. So you forced me to start this area. Sometimes when students come, I just tell them, okay, go ahead. And then I have to start learning with them. Someone said, learning is a continuous process. There is nothing like, I have finished learning. No. Learning is a continuous process. So the student actually asked me, sir, can we work in this area? Then we started around this time. We started working in this area and then try to develop our own materials. Some of them are good materials. So what we do, we actually, so my students make this kind of cells. Cell looks like this, and you make material, then you store you put the material here, and then you have the electrolyte, keyboard electrolyte, and then this is the diagram. Basically, this is inside this cellular cell. We have this arrangement. One can calculate all the energy density, power density, etc. So this is a book actually in 2017, methoxide capacitors. Our work is quoted extensively in this particular book. They have taken even the some of our figures are printed there. So those who are interested, you can actually see some of the references here. Some of the references, I don't know if you have access to library journals. Otherwise, if you are interested, you send an email. I can send you the paper, electronic version. Okay, so this is the story now. So for supercapacitor, you have carbons, polymers, oxides, ruthenium oxide. All these are people have been doing extensive research in these areas. So in 2008, that is the story. Right? You see, you don't see any nickel oxide here. Do you see any nickel oxide? There is one nickel oxide here, very small one here. It is only showing specific capacitance is very, very low, something like 50 farad per gram. The nickel oxide here. And then the nickel oxide, ruthenium oxide is something here up to 400, but it is a mixture of that. There is some nickel oxide here. These are showing around 300 and less. So we started looking at nickel oxide. Can we actually increase the capacitance of nickel oxide to very high value? So that is the starting point for us. So in the literature, if you see when you start working on a certain material, or certain problem, you pick up what you have to do, you have to go to the literature and see what has been done, how much has been understood in that area. So this one tells you a good electrochemical capacitance, a good material for electrochemical storage should have large surface area, porosity, ionic transport, instead of carbon, conductivity, nanosite morphology. All these things have to be inbuilt in the material so that you get the best out of that. Okay, so we have done that, and then finally we started looking at how to prepare that material. Once understood this, these are the things which we need to we should have these properties in the material. So now how do you get those properties into the material is the question. Now, when you are actually looking at the synthesis, material is obviously you have to synthesize it. You have to synthesize it. So in the synthesis part, so you are actually looking at all these properties, but then these properties depend on variety of parameters that you actually employ in your synthesis. For example, crystal, template, solvents, etc. All these things have to be taken care of, or you have to have some kind of a thinking and see how do I actually control these properties. So and then choose the required materials, required precursors to get that material. So the synthesis is a challenging thing. Synthesis is a challenging thing. So this is a review where people have actually done a lot of other things here, 1D material, 2D material, 3D material, etc. So if this is a journal, what we have done is we have looked at this, particularly we focus our attention on metal oxide, hydroxide, graphene metal oxide, hydroxide. These are the two areas which we chose, and we tried to look at the nickel oxide and then remaining other branches metal oxide. So when we started here in 1990, 96, 97, when we started this research, we had this nickel oxide. This is a nickel oxide, you can see here. This is nickel oxide example we are talking about, and then the theoretical capacitance estimated was 2500 farad per gram. But we were thinking only at very small value, so only 59 farad per gram. You see that weight, that is actually very, very low. Theoretically that was estimated. So how do you improve it? So for that we studied literature, and then we came to an understanding that now we have to do something differently, particularly the synthesis part. So now what we started looking at it, and we increased this 59 farad per gram to 239, 400 level, 420. Up to this point we were able to, these are our papers were published here. So this is up to 400 to 20 we could manage. We thought it would be difficult to go beyond that. But then here in another paper, 2014, they have increased it to 1700 farad per gram. So the point I am saying is, you have a material, so you need to cure it in such a way that you increase the property, right, and then use it for application. So that is something which is important. For that you need to have chemistry knowledge, you need to have the literature knowledge, and then properties, what kind of properties and how to use them. So that is a whole lot of things that you need to understand. Okay, so it was going on and on like that. So we made all kinds of materials like that. You can see here cobalt oxide, nickel oxide, cobalt sulfide, manganese oxide, and we substituted nickel in cobalt lattice, and then got this nickel cobalt oxide, and then zinc cobalt oxide, and many more. So we have done all that, and finally we ended up getting different capacitances. The highest strength one which we got was 1100 farad per gram. This one, and also 1400 farad, 420 farad per gram of this material. That is nickel cobalt oxide. Okay, so by tuning, by just looking at the synthesis part, changing the conditions, you achieve the best material. You synthesize best material for the required application. Okay, so this I will not bother you much about it, but this is a method to use it. This is a simple method, hydrothermal synthesis. This is only about 20,000 rupees. If you spend, you can get that this autoclave. It can be made, and then you have to have on a furnace, and then you need to have all these tables here. These are the surfactant molecules which we have used. So how do we actually now increase these properties of this material? What we have done is, first of all, we will try to increase the porosity. So what we have done is, we have used this surfactant molecules. Surfactant molecules have a head group and a tail. So these molecules will go on a drop, and then they make pores. Once you make these things will be inside. To remove them, you get a pore. Right? So that is the thing that we have done, and then we see that we have used out of the nanosheet. We were able to prepare flower-like nanosheets, flower-like materials out of the nanosheets, out of this nanosheet again by simply changing the surfactant. The T is the Niton X under the non-ionic surfactant, and then that C is the C gas, the ethyl ammonium bromide is a cationic surfactant. So these things are not very expensive, so you can use them. So what we did was that we took these things, we coated them. You can see this nickel foam. It's a nice nickel foam which you can buy in the market. And then this is the before deposition of this material. After deposition, you can see this nickel foam as a deposition of cobalt oxide. You can see that difference. Then the C of pictures. Okay. Another important thing is for super capacitor, you have to have pore size should be of the order of 2 to 5 or 6 nanometers. So we have got these materials with that pore size of 3.6 nanometers. That's very good. That is sufficient for us. So finally, what we have done is, so we have been able to get the materials with a capacitance of the order of nearly about 1600 farad, 16 or 1700 farad here, which we have been able to do. And then there are at the same time everybody was working on that, and people were making different types of materials across the globe. So we were able to get this one the best material here. This is the cheapest. It is better also. We don't have to spend a lot of money on that. And then what we have done is, next step is to have manganese oxide. The nickel oxide we stopped there, and then we went to look at the manganese oxide and we improve the capacitance of that. The manganese oxide, what we have done is we have taken the simple sugars, the glucose, galactose, mannose, sugars, which we have in the lab. Take these sugars and then take a manganese KML4 solution and then follow this procedure. So you get MnMnO2. But if you use different the sugar, you get different morphology. You can see the morphology here. This is a nice kind of rod, and this is slightly different, and this is the kind of folds. So you can see morphologies are different totally. you can make this material of different morphology, and then look at this one. So the whole diameter is from 5 to 1 to 5 nanometers. An angstrom. Nanometer, that means 10 angstroms. So you have a very good porosity here, and then I'm not too sure whether how you understand this, but so this is indication of porosity. If you have this is something like hysteresis. You must have heard of hysteresis in magnetism. How many of you know have hysteresis? Magnetic properties, you will see the hysteresis. So if you see this, that means the material is porous. Material is porous. We need to see this. You need to see this gap. Okay. So once we get that, then we study this capacitance. You can see here. This is this material, manganese oxide, which is made in nanos, is showing good capacitance here, specific capacitance. This is something like 320 farad per gram. So even by changing the precursor, you can actually get better material, better morphology, better material, which can give you better properties. Okay, so that is the essence of this. Then we have to look at other transition elements, vanadium oxide. Vanadium oxide is also another oxide which can be tried. Actually, here what we have done is again we prepared this vanadium oxide by using the surfactant, and we got vanadium nano chains. You can see this is a nano chain. Can you see the chains? Nice chains, nano chains. And whereas this one is here we have used the surfactant, whereas in this case there is no surfactant. It just simply V2O5 from the shell, from the lab. Whereas this one is synthesized. You can see the nice chains here. Okay. So these two materials, if you compare, that is, this should show better property. Now you can see here clearly this bulk V2O5, which is taken from the shell, does not have any hysteresis like this. That means there is no pores there. That will not be very good. Whereas if you see this red one here, which is surface area vector per gram, that one shows small hysteresis, and this black one shows really lot of hysteresis. So that is very good for us. The black one is nothing but this one. This material. Okay, that should give us good property, characteristic property. So we have measured that. Now we can see this is the one which is showing something like 600 above, around this value. Okay, so that's how we actually view the property of the material to use it for calculation. Okay. Now next what we have done is we have taken the cobalt oxide. There is another interesting oxide material for calculation. Here what we have done is we have just made this cobalt oxide as it is. We can see the nice nano sheets. We are able to see the nano sheets here. You can see beautiful sheets stacked like this sheet. Okay. Now this sheet, suppose if I take this cobalt oxide and then instead of 3, you put small amount of nickel with it. Cobalt oxide lattice, small amount of nickel. That is, you are actually putting 0.3 nickel into the cobalt. Cobalt is 2.7, nickel is 0.3. Otherwise, normally cobalt oxide is CO3, O4. So you insert nickel in the place of cobalt in the lattice, so you get this material. Immediately you change it from here to here. You see that? This is nice. This is a sheet, nano sheets. Change it to some kind of flowers here. See the changing. Immediately changes the morphology. So that is another thing which we have done. And this is coated on a nickel foam. So this is a pure nickel foam, and this is a coated nickel foam. You can see this coating is there. And that is selected for capacitance charge storage, and what we found is that you can see here, this is nickel 0.3 cobalt 2.1 oxide is giving something like 500 barrels per gram compared to normal CO3O4. There is huge jump in capacity. Right? So synthesis is very important. Synthesis parameters are important. Synthesis vectors are important. Synthesis temperature is also important. So if you can optimize this, it is not an easy task. It is not an easy task. But if you can optimize it, you can get the best material. Okay, so now the same thing, nickel substitution. Let me show you this graph where nickel cobalt oxide, somebody has done in 2013. What we have done is we have changed all those parameters. We have taken this all the way from 800 around 900 to we have taken it to something like 1600, almost double by changing the synthesis parameters. We doubled it, 1600 barrels per gram. So this some of these commercial people started asking me, can you give that process for commercial? Let me tell you, in Bangalore and many places in Chennai, people are actually starting startups to make super capacitors. They are ready to invest money, so much of money. Because there is a lot of commercial value in here. So here, what we have also done is that whether synthesis temperature has any effect on the morphology. So we have prepared this material at different temperatures, 120 degrees, 200 degrees centigrade. So here you can see again the morphologies are different. Morphologies are different. I'll show you that. This is the material which is prepared at 200 and 120 degrees centigrade. This is the material which is prepared at 200 degrees centigrade. That is yeah. So temperature also has an effect in morphology. Okay. So I think it's, let me just go a little fast actually here. So we went on studying many materials. For example, zinc cobalt oxide we have made. This is another material, zinc cobalt oxide, which is also very interesting there. So summary is to have this. You can have different materials, synthesis methods, surfactant effect of surfactant, which has very strong effect on surfactant and on morphology and the properties of the material. And also reducing sugars on manganese oxide has a lot of effect on that. And then you get different morphologies here. You can see in the case of cobalt oxide, okay, and so on and so forth. So the story here is synthesis is not an easy job that we need to focus on. Okay, so this is a story, earlier story. I take it for 5 minutes and finish it off. Then this is nickel cobalt chalcogranite. We actually shifted from oxide to chalcogranite. In chalcogranite, we looked at nickel cobalt chalcogranite, nickel cobalt, sulfur, selenium, tellurium. These are the chalcogranite. This is an oxide basically. You don't call it as chalcogranite. So here we have used this hydrothermal method and prepared this material. Okay. So you can see here, step 1 is basically the heat treatment, and then step 2 you have anion exchange process where you have hydrothermal synthesis, use it, and then you can use sodium telluride, sodium selenide, sodium sulfide. Using these precursors, you can synthesize nickel cobalt sulfide, nickel cobalt selenium, nickel cobalt tellurium. These are the 3 materials which we have studied. This is published in Dept Society just last year. So here we are using this setup here to prepare, to measure the properties of this. I just show you the final result of that. So here you can see this material. This one is showing very high power density, 20 to 50 watts per kilogram. Right, so you can actually increase it. However, the problem is this value has come down. This value has to go up a little bit. But this we have achieved 2250 is a huge number. So, but it, we still have to work on this because this value is low. Both we need to increase to have a good material. Okay, this is a comparison of other things, but this is where we are here. The color circles are around we have to pay. The last topic is meta-organal frameworks. These are meta-organal frameworks where you have a huge, the yellow one is a void basically, huge void. This void is 28.8 angstroms, 24.5 angstroms, huge void. These are the voids which we want because we need to use it as a porous material. So this another one, meta-organal framework, is the material which is there storage of even channels are there. These channels are also important because ions have to go there and then switch transport, ion transportation. So these materials are supposed to be very good for that. So I just skip this thing. What we made was, we made this meta-organal framework using lanthanide ions. Lanthanide, you are familiar with lanthanide, right? So lanthanide ions will give very good material because lanthanide can have coordinate number more than 4. Can have 5, 6, 7 or all. So that is very sort of material element which will give you this kind of porous material. Okay, so I just quickly show this that by using this material, this is cerium lanthanide, cerium MOF. You can see these are the batteries which are made using the cerium lanthanide. It is the LED is glowing here. Can you see that? The LED. You can actually build the LED in the lab and then they glow. Similarly, we have also used the chip system of another MOF. I just keep all these things because I'll show you the final version of that. So we have made again this block cell and then the cell and which we are showing you here. This is the LED which is glowing. It's the material that we made in the lab. You can see here, this is published in nanotechnology journal. You can see these all LEDs are glowing using those materials which we made in the lab. Okay? So these are the people who have done this work. He is in Germany, he is in NIT Warangal. Somebody is there from NIT Warangal? So he is in NIT Warangal, he is in NIT Jaipur. So these are the guys who actually made me work in this area. So I must thank them. So the story is changing very rapidly. 2008, that is the story. 2015, this is the story. We have a lot of new materials. 2022, I have to make that I have not made yet. So what is the take-home message that I want to give you is that designing materials, synthesis is very important. Particularly I am focusing on the context of energy storage materials. So synthesis parameters are critical. It's not very you cannot predict them. Predicting is very difficult, but you have to really do a lot of work and then bring out some principles from that and for the repetition. You need to be able to predict. For example, I use these conditions and I should get this. That prediction is still difficult now. But in the future, and as you keep working on that, to bring out principles, you will be able to figure out that. The structure morphology of materials greater than the function. I told you a lot of examples. If you change the morphology, structure morphology, you change, you are able to increase the property and reduce the property. Understanding structure and function relationship is very important in material science. What is the structure? What is the function? This relationship has to be understood thoroughly so that you can apply it. Okay? And then you need to be able to design these functions rationally, that is given a big challenge, big challenge, even though you have been working for decades, you still have a lot of challenges to address. So this is the group, and these people are working differently. So this is, he is working on hydrogen director, he is working on supercapacitor, she is working on supercapacitor A, and she is working on water splitting, she is working on that. He is working on water splitting at high temperatures. He is a joint unit of chemistry department, mechanical engineering, and she is working on mechanical frameworks. She is working on carbon materials, and these are all MSc students. Some of them are MSc students, and some of them are postdocs. So that's the story that I can tell you. Okay. And thank the funding. I get money from Ministry of Human Renewable Energy and Information Technologies, Ministry of Human Resource Development, Science, Industry, Science Engineering Research Board, DSIR, DRDO. All these, I tell you, all these are waiting for you to finish your PhDs and then ask for money to do this research. Particularly for women, a lot of new schemes are coming. Okay? So all of you should look for such opportunities and then study hard and come up with new ideas this stage. Okay? So thank you. Any questions are there? Any questions?
Yes, if anyone want to ask any questions, you can.
You are all agree?